Hello, Dave Brown back again, this time with Basic Electricity Part 2. Now, we're going to have a further discussion of AC, or alternating current. And as we stated in Basic Electricity Part 1, AC, or alternating current, is current that flows first in one direction and then in the other. This change in direction is very rapid. Usually 120 times or 60 complete cycles each second, from positive to negative and back again. We can actually see this action on a device which is much like a TV screen and is called an oscilloscope. The picture looks like this, with this point being the maximum positive and this the maximum negative. And the time from here to here is 1/60th of a second. 60 cycle is the most commonly used current in this country. However, 50 cycle is used in some sections and in many foreign countries. Occasionally, some others, such as 25, is used. Another word which means cycle is hertz. And in recent years, this term has come into more common usage, so that today either may be used. Cycle is frequently shortened to CY, while HZ is used for hertz. The chief advantage that AC current has over DC is the fact it can be changed from high voltage to low voltage and then back again as necessary by the use of a simple device called a transformer. If you've ever operated an electric train, then you're already familiar with the use of a transformer, even though you may not understand its operation. This little heavy box, which has the controls on it, is a transformer. Again, the transformer on the light pole is a common sight, and yet most people don't realize how it works or why. One of the more basic configurations for a transformer looks like this, where we have a laminated core, which means we have a stack of thin sheets which have been punched out like this. If around one side we loop a wire 10 times, and around this side 5 loops, now if we make the 10 loop side the primary or input side, we will get 1/2 the voltage on the output or secondary side as we put in here. This is known as a step-down transformer. For example, if we put in 240 volts here, we will get out 120 volts here. If we reverse it and make this side the primary, then we have what is known as a step-up transformer. And if we put 240 volts in here, we will get out 480 volts here. By varying the number of loops on either or both the primary and secondary, the desired output voltage can be obtained. A transformer is very efficient, which means there is very little loss of power in its use. And here is what a small standard transformer looks like. Okay, now you're wondering what's so great about being able to change voltage around. Well, let's look at Ohm's law again. E equals I times R. Also, let's look at our example of 120 volts and 12 amps current. The resistance of 10 ohms is for a certain length of wire. Now, say we move our power requirement, whatever it is, on the other side of town, say 10 times as far away, and we use the same size and kind of wire. Then what happens? Let's look at our equation. We still have 120 volts, but our wire is 10 times as long as it was, and our resistance will be 10 times as much, or 100 ohms, because resistance in a given wire is directly proportional to its length. That is, double the wire length, and you will double the resistance. As you see, since our input voltage is still 120, and our resistance has increased because the wire is longer, the amperage will have to be less to keep the equation in balance. In actual practice, what will happen is that the output voltage will be less as well as the amperage, which further aggravates the problem. This loss of voltage is called voltage drop. The analogy of pressure and flow in a pipe further illustrates this relation. If a pipe is made 10 times longer, there will be more resistance, less flow, and less pressure at the output end. Okay, so what's to do? If we have a DC system, the only thing we can do is use a larger wire here, which would have less resistance, since resistance is inversely proportional to wire cross-section. That is, the larger the wire diameter, the more amperage it will carry. With AC, however, we have another choice. Here, we simply put a 10-to-1 step-up transformer in the system right after the generator and boost the voltage up from 120 to 1200. Now our equation is the same. I equals E over R. Amperage equals 1200 divided by 100 equals 12 amps. Now that we've transmitted the power, we use a 10-to-1 step-down transformer, and we have the 120 volts and 12 amps, and we've transmitted over a long distance without having to have a larger wire. This property of AC current is what allows us to have interconnecting power systems, which transmit power over high voltage lines for hundreds of miles. There are two kinds of AC current, single phase and three-phase. Single phase is what is used in most homes. This is the kind of current that we were looking at with this sketch of a sine wave curve. Single phase is normally either 120 or 240 volt. These voltages are approximate and may vary slightly depending on the section of the country. With this system, we have 2 wires for the 120 volt and 3 wires for 240 volt. With 120 volt single phase, 1 wire is the power, or as it's usually called, the hot wire. The other is what is known as the neutral. It should be noted here that most electrical appliances now have a 3rd wire, which is the ground wire. It serves as a safety in the event of an internal short. The ground is connected to this prong here on a 3-prong plug. When we connect a load, such as this light bulb across the system, it lights up. The resistance to flow in the filament causes it to heat up, and it gets hot enough to give off light as well as heat. Since this is a 60-watt bulb, then it will use 1/2 amp current at 120 volts. If we put another 60-watt light bulb here, it will also light up just as bright as the first one. This is what is known as parallel circuits. Most wiring is done using parallel circuits. If we take the 2 bulbs and connect them like this, they are in what is known as a series connection. And as you see, they won't burn as bright as before. This is because we now have doubled the resistance in the line, which in turn has cut the amperage in half. We could have predicted this would happen from Ohm's law. E equals I times R. Voltage equals amps times resistance. So if voltage stays the same while the resistance is doubled, then current will have to be cut in half to keep the equation balanced. A 240 volt single phase circuit has 2 hot wires and 1 ground wire. Voltage between either of the 2 hot wires and the ground wire is 120. But between the 2 hot wires, the voltage is 240. 240 is normally used on heavy loads such as electric stoves and air conditioning units because it requires smaller wires than if 120 volt were used. The generation of 3-phase electricity in its simplest form is the same as this sketch for single phase, except now we rotate 3 loops in the magnetic field instead of 1. There's 1 here, 1 here, and 1 here. These are spaced equally so that there is exactly 120 degrees between them. Now each loop in turn generates a curve, just like this single-phase curve, which by the way is called a sine wave. But since all the loops are rotating at the same time, their curves are superimposed on each other. That is, they are placed one on top of the other so that they form sine wave curves like this. This white line is the curve generated by the white loop. The green loop generates the green curve, and the blue loop, the blue curve. You will note that each reaches a peak 120 degrees from the other. 120 degrees from here to here. The peak is reached when each loop is at the center of the magnet, where the magnetic field is strongest. The negative peak is reached when the loop has turned 180 degrees from the positive peak, and the EMF is at a maximum in the opposite direction. Three-phase systems usually have three wires, all of which are power or so-called hot wires, and all of which are normally connected to the load. Some systems employ four wires, one of which is a ground. When calculating power on a three-phase system, the normal power formula must be modified to read P equals 1.73 times IE. Note that the multiplier 1.73 has now been added to the power formula. Thus, if we have a three-phase system and we check with an ammeter and find the amperage is 20, and with a voltmeter we find the voltage to be 480, then P in watts equals 1.73 times I in amps times E in volts, or P equals 1.73 times 20 times 480. Therefore, P equals 16,608 watts. Since 746 watts equal 1 horsepower, if we want to express our answer in horsepower, it would be 16,608 divided by 746 equals 22.26 horsepower, or HP. The three-phase current found in most industrial plants is usually either 240 or 480 volt. However, other voltages are occasionally used in some sections of the country. For example, 208, 550, 2400, and 4000. These voltages are approximate, as in the case of single phase, since some locales are, for example, using 220 or 230 instead of 240. Practically all industrial installations are three-phase. Two-phase can be generated by simply having two loops, as you see here, instead of three. But two-phase is rarely used anymore. Most electrical wiring is governed by a set of standards called the National Electrical Code. The code is in book form, and this is a copy. These standards are usually used to govern such things as how large the wire used in a plant must be. And most local building laws, which are called building codes, specify that the wiring used must comply with the National Electrical Code. At this point, I should mention that fuses and/or circuit breakers are protection devices used in a circuit to prevent more current flowing than the wire or some other component in the system can handle. The standard fuse is designed to burn out when a certain freedom... Since we mentioned wire sizes, let's discuss them for a moment. The wire diameters are usually identified by the AWG gauge size, and AWG stands for American Wire Gauge. These are identified by numbers which start at number 40 for the smallest, which is about like a hair, and as the wire gets larger, the number gets smaller down through 4/0. This is number 20, which is what is used for doorbells and other low-voltage wiring. The term low voltage is normally used on circuits of 24 volts and less. This is a piece of number 14, which is the smallest size permitted by the code to be used in house wiring. Here is a sample of 4/0. The next wire size larger than 4/0 is 250. And from this point, as the size number gets larger, the wire gets larger. 300, 350, and so on. This is a 500. Stranded wire is usually used in the larger sizes, but this is primarily to make the wire more flexible and to allow a steel center core like this, which makes a stronger wire for spanning long distances. Exact diameters and amperage capacities for various insulation types are spelled out in the National Electrical Code. Normally, identification is printed on the outside of the insulation, with wire size first, then this is followed by some letters. The letters stand for the type of insulation used on that particular wire. Earlier, we showed how current flowing through a wire caused a magnetic field to be created. When several loops of wire are close together, their magnetic fields tend to reinforce each other and create what is sometimes referred to as a suck coil. A suck coil is the common solenoid coil like this, and the name suck coil is derived from the fact that when a piece of iron is brought near to it, the iron tends to be sucked into the coil. Let's look at that again a couple of times. This unit's property is used in items such as the solenoid valve, like this. Or it's also used in relays, like this one. These items are used in most every industrial plant. Earlier, we mentioned resistance to flow in a wire and how this is a problem when we are trying to transmit power over long distances. This same property, which causes a wire to heat up and is a problem, is, however, useful in other applications. We've already mentioned the filament in a light bulb, but this same basic property is used in resistance heaters of all types, in kitchen stoves, in electric skillets such as this one. It's also used in home irons, in industrial furnaces, as well as many other applications. In recent years, resistance heating has become even more important since it is pollution-free at its point of use, unless, of course, the heat itself is considered to be pollution. Of all the industrial uses of electricity, the place where it is most commonly and widely used is in electric motors. We won't discuss them further at this time since they are covered in Teletrain's tapes Motors 1 and 2. Let's briefly summarize our discussion. Although it's difficult to define electricity in absolute terms, we can describe electricity as a source of energy which flows along a conductor by shifting electrons from one atom to another along that conductor. This shifting action is almost instantaneous, that is, 186,000 miles per second. Next, Ohm's law states that voltage equals current times resistance. The power law states that power equals current times voltage and can be remembered with the pie chart. An electromotive force, or EMF, is generated in several different ways. 1. Friction, rubbing glass with silk. 2. Mechanically, moving a coil through a magnetic field. 3. Chemically, action of a liquid or paste on metals. 4. photocell, result of light on light-sensitive materials. 5. Thermoelectric, heat applied to the junction of two dissimilar metals. 6. Piezoelectric, pressure on certain crystals. A simple transformer was discussed. Next, we discussed AC current and how the transformer is used to allow us to carry large power requirements over small lines. Three-phase and single-phase current were identified and their common use explained. The National Electrical Code is the standard used for most electrical work. Solenoid coils are created by several loops of wire wound closely together. Resistance heating, although a problem when carrying current long distances, is important in many applications where heat is desired. Although we have no exact definition of electricity, hopefully you now have a better understanding of it and a background of what it can do. This concludes Teletrain's tape on basic electricity.